So we are streaming now. Thank you for the reminder. And so if there are no questions about Dijkstra's algorithm, we are going to move on to talk about the A-star algorithm. Okay. So let me go find the class first because they keep moving these things around. Okay, right here. Nope, this is the fall version of this class. There we go. All right, so getting back to graphs. And what we'll do this time is to look at the A-star algorithm. So Dijkstra's algorithm is done. Okay, I tracked it down once, and you guys can see how it works. So here we have the A-star algorithm. The A-star algorithm, which is A and then the asterisk symbol, is also an algorithm to find the shortest path, but this one is quite different from the one that we have worked with. This one searches for a shortest route from a vertex to another vertex. Okay, so technically speaking, the algorithm itself can only account for one single destination, and you have to tell it where you're starting, and it will find the shortest path between those two vertices. So this is a big difference compared to Dijkstra's algorithm, because Dijkstra's algorithm will find the shortest path from every vertex to every destination vertex, and you can have multiple destination vertices. This one only has one single destination vertex, and you can only figure out the shortest path from one single start vertex to the destination vertex. And then the second thing about A-star that is different is it makes use of a heuristic function. A heuristic function is an estimate. It is usually the heuristic function is very fast to evaluate. It doesn't take much time, and it always gives you, an underestimate of the actual shortest distance. So the key here is the heuristic has to be quote unquote admissible. Admissible in this case means it is always an underestimate. Are we still doing okay so far with those concepts? Okay. Okay, so me.
No, seriously, I do have a question because when I was looking into it, when you said that it's called, is it the A-stroke algorithm or the A-star algorithm?
Well, right before you came in, we already said that.
Okay, it's A-stroke?
A-star. So maybe be more on time next time.
It's the second one. Gotcha, yeah. No, no, but seriously, so what happened is when I was doing some experiments, they made it look linear. Like I was doing some practice once online, and they made instead of having like how we did the other algorithm.
No, A-star is kind of not linear,
Okay.
but it's not that different from Dijkstra in a sense that it is quote unquote breadth first search, but it also integrates the use of a heuristic function.
Okay.
Yep.
I didn't quite get what you meant by like heuristic function exactly.
A heuristic function is a very simple function that you can evaluate in a very short amount of time, and it gives you an underestimate of the shortest path or the length of the shortest path.
So it will give you like, well, what does it mean in like that context? Like underestimate.
So it's a trade-off of speed for accuracy.
But like in what way would it be like inaccurate?
Okay, so let's see whether we can use these notations to kind of help us out. The heuristic function is basically mapping a pair of vertices to a real number. Now, in reality, we don't really care about most of the pairing of the vertices, only the vertices to the destination. In other words, the second set, usually you don't really need it to be the entire set of all the vertices. It can be just the set of the destination vertex. But for completeness purposes, the heuristic function should be evaluable, across all pairs of vertices. And it maps to a non-negative real number. So everything, all the lengths and distances have to be non-negative because negative length or negative distances would give us a lot of issues. So we always want it to be non-negative. So on the other hand, if I define another function called L, and L is actually going to give you the actual shortest path between two vertices, then we want the heuristic function to be always less than or equal to the L function. Now the easiest way to do this is, oh, we'll just define h of whatever to 0. That's a valid, heuristic function. It doesn't do you any good, but it is, nonetheless a valid admissible heuristic function. So is that okay? All right. So that's basically what I said, in this particular paragraph is, you can define the heuristic function to always return 0, and it is valid. It is still admissible even though it is not going to give you any additional information. So this is the actual algorithm here. I kind of add in a lot of notes to explain what we are dealing with. So we'll deal with this. We'll explain this line by line or item by item here. The graph is still represented the same way, which is G, and G is a two-tuple. It has a set of vertices and also a set of edges amongst the vertices. So from that perspective, it's the same as the as Dijkstra's algorithm. The distance function, same way, we are just having a function that maps every single edge to a non-negative real number. Can be 0, okay, but most of the time it is not 0 and it cannot be negative. So the first 2 points should not be a surprise because we have the same type of symbols for Dijkstra's algorithm. The third one is a little bit different because in this case we have to define a single start vertex. Unlike Dijkstra's algorithm, which has basically no idea of, oh, so where are you starting? You don't have to specify. So in this case, we do have to specify a start vertex. And there's really not a whole lot of easy way to say, okay, but I want all of these, vertices to be the start vertex. And what I said here, the easiest solution is to have zero distance edges leading from a virtual start vertex to all the actual start vertices. Actually doesn't work. Okay, unfortunately, it will only find the shortest path. Well, okay, I take it back. It will work in the sense that you can say, okay, how should I put it? It is not, in a sense, truly equivalent to having multiple start vertices, but it will tell you which one of the alternative start vertices actually is shortest, has the shortest length to the destination. So it doesn't find the shortest path from every single start vertex to the destination, but it will tell you which alternative is the shortest. I'm not sure whether that's helping or not. Is it helping or not? Yep. Just one. It will only give you one. Yep. 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 So it doesn't help that much. It's not equivalent to Dijkstra's algorithm in any way. Okay. It also has only one single destination. So in this particular notation, I use x. X marks the spot, right? So I'm going to use it as my symbol for the destination vertex. But in this case, you can make it so that it has multiple actual destinations. Basically, all the actual destinations have a zero cost edge to a virtual destination. So that way you can basically designate a whole bunch of vertices to be quote unquote the destination, and then the algorithm will just find the shortest path to one of the quote unquote actual destinations. Yep.
Will it be doing it one at a time? Because it can only do one vertex and start vertex.
What do you mean by one at a time?
Like, will it run over again to do the
No.
next vertex?
It will find a single shortest path from the start vertex to one destination vertex out of the vertices.
But if you have more destination vertices,
It ignores the rest. It will find the shortest path to one. It will find the shortest path to the destination that is closest to the start vertex, and the rest it doesn't. It will not be a part of the solution. Yep.
Can this also be applied to not just only find destination, but find network protocols?
No.
Can you use it like that?
It finds it basically finds the shortest path or one of the shortest paths from a start vertex to a destination vertex. You have to designate one vertex as the start, one vertex as the destination. And it will find the shortest path between those two. So it's not the same as Dijkstra's algorithm.
Oh, okay. So this is okay. Thank you.
Is it possible for this algorithm to come up with what it thinks is the shortest path, but it's actually longer path than what Dijkstra's would find from the same data set?
That should not be the case, but you have to make sure that the heuristic function is admissible, which means it is always an underestimate of the actual length of the shortest path. As long as that requirement is met, it always guarantees to find the shortest path. Okay? Yep.
So if this is gonna so you had the multiple endpoints or whatever,
Mm-hmm.
this is always gonna find the shortest path to the closest
Endpoint. Correct.
Why do you want the other algorithm? Is in the other case we were still looking for the shortest path to the closest thing, right?
The other one, you mean Dijkstra's algorithm. Dijkstra's algorithm will find the shortest path to a destination for all vertices.
So you can change if you want to change. Oh, we want to go there now. It will be able to handle that.
You don't have to run the algorithm again if you change your start vertex. Whereas with this one, it will only find the shortest path from a single vertex to a destination. Yep.
It's like from A to B.
Yep, you have to say what is A and what is B. The other one basically says, okay, tell me the potential destinations and tell me potentially where you can start, and it will find the shortest paths from every single point to a destination. Yep.
So this algorithm, like algorithm, would be the Google giving the directions from your current point to the destination, right?
Correct. So the A-star algorithm can be used to find the shortest path or the quickest route from one point to another point. But it doesn't take into consideration, like, are you going to pay toll? Are you going to go through private roads and stuff like that? So all the optional switches they can use in Google Maps, they're not inherently a part of the A-star algorithm. Now, maybe you can modify the algorithm to take those into consideration, but it is not inherently a part of the A-star algorithm. But if your only concern is about time, it will find the path that will take the least amount of time, assuming you have all the data between the vertices. Okay. Not necessarily. It depends on whether the freeway is congested or not. Yep. So any other questions about what we have already discussed about the A-star algorithm? Okay, so once again, we got a few symbols here. V is the set of vertices, E is the set of all the edges, D is a distance function mapping each edge, which is directed to a non-negative real number. Lowercase s is the start vertex, lowercase x is the destination vertex, and then lowercase h is the heuristic function. And the heuristic function, in order for A-star algorithm to work correctly, the heuristic function has to be admissible, which means it is always going to be an underestimate of the actual length of the shortest path between two vertices. So the initialization is here. So for each vertex in V, we have to define two functions. One function is called G, and the other one is called F. You can probably rename those things to make more sense. But just to explain what the G function is, G of V is basically the actual length of the shortest known path from S to V, from the start vertex to that particular vertex. Is that okay? It is kind of like the L function for Dijkstra's algorithm, except this one is from the start vertex to whatever vertex we have in mind here. Is that okay? So let's see how it is initialized. If V is not the start vertex, then I'll just make the assumption of infinity. Because I have not explored the map yet, so I'm going to make the assumption that this vertex V, which is not a start vertex, is not even connected to the start vertex. So I will update it when I find a way to connect it, but the assumption is it is not connected. On the other hand, if V does equal to S, then g of s, in this case, is 0. Because how far away is the start vertex from itself? 0. There's no distance between the start vertex and itself. Is that okay? Okay. So f is interesting too. F is basically, I used the wrong symbol here. This should be f. F of v is the estimation of the length of the shortest path from s through v to x. So it basically has two components. The first component is g of v, which is the actual known shortest path from the start vertex to the vertex v. The second component is the heuristic from vertex v to vertex x, which is our destination. So basically it has two components. So are we still doing okay so far with this? Or do you guys want to have a little picture to illustrate it? I think a picture is going to be helpful. So let me set up the tablet. And so we'll go to Chrome apps. There we go. All right, so we have a single start vertex that I call, vertex S. We have a single end vertex or destination vertex that I call X. So now we have some vertex V that we are considering. So the vertex V here, the known shortest path or the length of the known shortest path from S to V is what I call G of V. Okay? So that's actual. It is not an underestimate. This is the actual length of the shortest path from the start vertex to whatever vertex V we are considering. And then we have h of v. So h of v is basically saying, okay, if I start from vertex S, go through vertex V, and estimating, how much distance we still need in order to go from vertex V to vertex X, what is the estimated, it's not h, sorry again, this is f of v. I keep using the heuristic function itself. This is f of v. So f of v is basically the distance, the estimated length of the shortest path from the start vertex going through vertex V to the destination vertex. Is that okay? Yep. Yes. So basically the way we are doing in the algorithm is we are saying for every single vertex lowercase v in uppercase V, we are doing the initialization. And the initialization is saying, okay, if V is not S, we'll just use infinity for G and also F. Because we have not explored a single thing, we cannot even confirm that there is a way to go from vertex S through to V, so we cannot actually use any actual value here. On the other hand, if V does equal to S, we go to the else case, and then we initialize G of S to 0, because the start vertex is a 0 distance away from itself. Yep.
So, where it says v not equal to else, the second f of v is infinity. H of v, is that correct?
This one is supposed to be f of v. So f of v is the estimation of the length of the shortest path from S through V to X. So let me fix that, because I don't like this to be. Say again?
The one below it.
And which module is this? 310. The other one is correct. Okay, so we'll get to that one. And we want to look for estimation of the length. Okay, so uh-oh. Okay, there we go. That's the correct one. Change this to F. It's LaTeX. LaTeX. And we're just republishing the document and Control R to update. Okay, so now it is updated. Okay, so now we look into this one here. This is the initialization of f of s, because we don't get to the else branch unless v and s are exactly the same thing. So we are basically initializing f of s. F of s, by definition, because it has the same definition of, as above, it is the estimated length of the shortest path from the start vertex through the start vertex to the destination. Well, we do have the heuristic function for that. So it basically is the h, or the heuristic function value, from the start vertex to the destination vertex itself. And remember, that should be an underestimate of the actual length of that path. Is that okay so far? Are there any questions up to the initialization of the g and also the f value of a vertex? No questions? Okay. So if there are no questions, we move on to a previous function. So the previous function is another way to keep track of E prime. So in Dijkstra's algorithm, I use E prime as a set of edges to keep track of the solution graph. In this case, I'm just using a previous function. So the previous function is asking, in the shortest path, in the actual shortest path, what vertex is supposed to be right before vertex V? And it is defined to be, it's undefined, because we have not explored a single edge, so we do not know a single part of the solution graph. So it is basically undefined. Is that okay so far? Okay. Yep. Do I update? Okay, so the lowercase v is the variable to go through all the vertices in the set uppercase V. So from that perspective, I'm just saying, okay, look at every single vertex in the set of all the vertices and do some initializations. So I have to initialize 3 things for each vertex. I have to initialize the g value, the f value, and also the previous vertex of a particular vertex. Is that part okay so far? Okay. So if that is okay, we now define O. Okay, so once again, we have a set called O. It is defined to be the set of just the start vertex. Okay. And this part is different from Dijkstra's algorithm, because with Dijkstra's algorithm, we start with all the destination vertices. This one starts with the single start vertex. So we are always starting from the start vertex itself. And then what we are doing in this loop is a little bit it takes a little bit more explanation now. So we look into O, and then we say, as long as the uppercase O set is non-empty, and we also want to make sure that there is at least one vertex V in the set of all the vertices, such that f of V is less than g of x, do the following. That doesn't seem to make sense. Oh, okay, that makes sense. Okay, so g of x, this x is our destination vertex. So we're basically looking at every single vertex V and say, do we have one vertex V so that the estimated path, length of the path from the start vertex through V to the destination vertex is less than the the length of the known shortest path to the destination vertex. think I might have gotten this part wrong a little bit. I think this is supposed to be g of s and not g of x. Nope, it is g of x. Okay, never mind. Because I defined the g value to be the length of the shortest path from the start vertex to that particular vertex here. So g of x is really the length of the known shortest path. So when you combine these two statements together, it is basically saying as long as there's one promising vertex that might actually give us a path that is shorter than the one that we have found so far, let's continue. So are we still doing okay so far with this algorithm? More or less? Okay. But does this make sense to you, as a conjunction, as part of the condition to stay in the loop? In other words, if this condition is false, okay, if I cannot find any vertex so that f of v is less than g of x, it's time for me to exit the loop. Does that make sense to you? It should make sense, okay, because f of v is always an underestimate of the length of the path to go from the start vertex s through vertex v to the destination vertex. So the actual length of that path is going to be at least as much as f of v. So if every single f of v, if the f value of every single vertex is greater than or equal to the actual length of the shortest path already found, then there's nothing that I need to explore at that point. Is that okay? All right. Okay. So, because O being non-empty is one of the conditions, so now we can say, well, we can find at least one vertex, but there might be multiple vertices in O. So how do we select it? Well, we just look for the one that is the most promising. How do we find the one that is the most promising? So we basically say for each, so we find the vertex in uppercase O such that for every single vertex in uppercase O, f of c is less than or equal to f of w. In other words, we find the vertex in O that has the least f value. Tell me again, what is the f value? Just in, huh? It's an estimation. It's an estimation of the shortest path from the start vertex through V to the destination. So I'm basically saying, okay, amongst all the vertices in uppercase O, which one looks the most promising? That's basically what it's asking. Okay? So this kind of algorithm, Dijkstra included, is called a greedy algorithm.
I heard that term before. It was at Stanford.
Hmm?
It was at Stanford and MIT. I heard that term before.
Yep. It's called a greedy algorithm because it's just saying, okay, I'm going to be aggressive and look for the most promising option to explore first. So the next statement is really just saying, okay, let's take that vertex C out of uppercase O because now we are quote unquote expanding it, we're considering it. And then the loop here, the for each loop here, is now looking at each neighbor of the vertex C. But it is also different from the for each loop inside Dijkstra's algorithm. In Dijkstra's algorithm, we're looking for all the incoming neighbors. This is looking at all the outgoing neighbors. So the direction is actually opposite to the other algorithm. Is that okay? All right. So it's basically saying for each outgoing neighbor of C, we call that neighbor N, let's go ahead and consider the following. The first thing we do is we compute a value. The whole reason why I put it into a local variable t is because we need to refer to that multiple times, so there's no need to compute it multiple times. So the focus is basically this part here. What are we looking at when we look at g of c plus the distance of the edge Cn? What is that telling me? It's telling me the length, the actual length of a path going from the start vertex through vertex C to vertex N. Is that making any sense? Because GC, or G of C, is the length of the shortest, known shortest path from the start vertex to vertex C. That's what GC is. And then DCN is the distance of the edge CN. So by adding these two, now I have the length of a path going from the start vertex through vertex C to vertex N. Is that making any sense? Now I said just one because there may be multiple paths from the start vertex to vertex N, but this is the length of one of those paths. In the next statement, I compare T to G of N. So this comparison is really asking, have we found a shorter path to go from the start vertex to vertex N? Does that make sense? Because G of N is the length of the known shortest path from the start vertex to vertex N. So if T, which is the length of one path, an alternative path from the start vertex through C to N, is actually shorter, then we got some work to do, because now we say, oh, what we thought was the shortest path from a start vertex to vertex N was not the shortest. Let's update something. So from that perspective, the conditional statement does about the same thing as Dijkstra's algorithm's conditional statement, except the direction is kind of like opposite. So then the next thing we want to do is to perform these operations, which are very similar to what Dijkstra's algorithm does. First thing is we add n, which is the neighbor of vertex C, into uppercase O. Because anyone who has the G value just updated needs to go back into uppercase O, because that can impact some of the other vertices. Is that making any sense? Okay. We also want to use this notation here to kind of remember something about the solution graph, but it is a different way to represent the solution graph compared to E prime. So this way, pref, is basically a function, and I'm changing the previous of n to C from whatever it was before. Is that okay? Because the shortest path to N is now going through C. So the previous vertex of N should be C now. Is that okay? All right. And then the next one here is updating G of N, because, hey, the length of the shortest known path before was not actually the length of the shortest path. I just found a shorter path from the start vertex to vertex N, so let's update the length of the known shortest path from the start vertex to vertex N. So that's why Gn is getting the value of T. And then the last one is I have to update f of n too. F of n is used to prioritize which vertex are we going to get out of uppercase O. So we have to update. We have to keep updating, the f value of the vertices. So f of n is g of n, which is the length of the shortest, the currently known shortest path from the start vertex to vertex n. So that's what gn is, plus the heuristic function applied to nx, which is the underestimate of the length of the remaining path from vertex n to vertex x, which is our destination. So we add those two, we add up these two numbers, then it becomes f of n, which is nothing more than an underestimate of the shortest path going from the start vertex through n this time to the destination vertex. Is that okay? I hope so. And then when this is all done, okay, this is the last part of the conditional statement, which is the last part of the for loop, which is the last part of the while loop. So when the while loop is done, which typically means either O is empty, which means okay, we have considered everything possible and we're done. Or the other condition is true, which means, well, we might still have some vertices in O, but none of those is going to be promising, because none of those even has a chance of being a path that is shorter than something that we have found already. So if those conditions, if one of those two conditions is true, then we can exit the loop. Okay. So when we get down to the last part of the algorithm, it really is just looking at the prev function to define the solution graph. So we are basically saying for each vertex in V, okay, we'll look at the prev function. And we say if the prev function, okay, I made a mistake here. This should be a prev V equals to W, or prev W should be V. So this W here is supposed to be V. Let me fix that too. It's the last one. And it's LaTeX. It spells like LATEX, like latex, but it's pronounced LaTeX. LATEX. It is actually LA tau epsilon chi, and therefore it is pronounced LaTeX. But in uppercase, so they look like TEX. Okay, going back to the browser right there. Refresh. Okay, so I got it right this time. So for every single W in V, we look at its previous value. If the previous value of W is V, then we make a new edge, or we make the edge of VW, and we put it into the solution graph E. I call E SX, SX as suffix, because it is the solution graph of the shortest path from vertex S to vertex X. So that's why I call it E SX. Sounds like an accurate model, but it's not. sounds like a mixture of Luxus and an Acura. Because ES is a destination in Luxus, and then all the Acuras like to end with an X, right? So. There'll be a great emblem that you put onto a Hyundai.
Oh wow!
Like a subcompact in a Hyundai, just put on the emblem of ESX. Yep. So are we good with this so far? Yep. Yes, we're going to do it. Now, it's going to be a little bit more complex with the A-star algorithm because we have to define the heuristic function from every single vertex to the destination at least. Okay. Yep. Question? Nope. Okay, no problem. All right. So let's go ahead and make an example. Okay, so that we can track this down, so that we can actually use the algorithm and find out what the algorithm is going to do. So this is over here. This is our start vertex. This is our destination vertex. Okay, so we'll put some vertices in between. Okay, so we'll put I'm making this up as we go. So once again, the number on an edge itself is the distance of the edge. Okay, so we're going to make the edges like this, and then we'll start to put actual distance values onto the edges. So let's say we have a 3, 1, 2, and we'll make this one a 4, and then a 5 here, and then 1 here, and a 4, and this is a 2, this is a 1, and that's a 1, 2. Okay. But then we also have to define the heuristic functions now. That's going to be the time-consuming part, um, because we have to make sure that the heuristic function is always an underestimate. Okay, it can be the same, but it cannot exceed the actual length of the shortest path from a vertex to the destination. So that's the constraint. Okay, so we'll define h of Sx. So what is the actual length from the start vertex to the destination vertex? I mean, you can just eyeball this one. I mean, you can. So we got 6, 6. We got two paths of 6. Okay, so I think 6 is the shortest path, or the length of the shortest path. There are two, because you can either go 3, 1, 2, which has a length of 6. You can also go 5, 1, which also has a length of 6. Okay, so there are two paths with equal length, which is okay. It's not a problem. So we can say that the heuristic, as long as this is less than or equal to 6, we're good. It can be 6 itself. Okay, as long as it's not exceeding 6, we should be fine. So let's make this a 4. And then we look at, okay, so now we have to label the vertices. This is A, this is B. We use vertex C in the algorithm itself, so I'm going to skip C and D, because D is the distance function. So the next one is going to be E. We use F, G as function names too, so we'll skip those two. H also, and then we have I, which looks like I is not good, J is okay, and K is okay too. I'm just avoiding things that are confusing or look similar to numbers or digits and stuff like that. Yep.
So the heuristic function chooses this first step to go.
No, the heuristic function in this case is defined, but in reality, the heuristic function is something that you compute, but it would be something that's easy to compute.
Because you put 4 over there and you said that the shortest is 6. Did you, like, at the end, did you make it choose 4? Or?
No, I just randomly pick a number that is less than or equal to 6. I could have chosen like 2 or 5, but I cannot use negative values. So as long as it is less than or equal to 6, but greater than or equal to 0, I'm good. The algorithm will still work. Okay, so I have to define what is AX now. So AX has to be less than or equal to 3. So let's make that 2. BX has to be less than or equal to 2, and we can make it a 1. And then EX has to be less than or equal to 1. We can make it exact. Okay, 1 is fine. It can be exact. And then we got JX. And JX has to be less than or equal to 3. So we can make it 2. And then we have KX, which is less than or equal to 1. Well, we can make it 0. It can be 0. You can make all of them 0. But if you make all of them 0, then Dijkstra's algorithm, A star basically becomes quote unquote Dijkstra's algorithm, because it becomes just completely just breadth first search. Because you're not getting any information from your heuristic functions. So are we okay so far? The definition. This is different from Dijkstra's algorithm in the sense that Dijkstra's algorithm has no need of a heuristic function. But A star, the best thing about A star is the heuristic function is supposed to help you explore fewer options, because the heuristic function should tell you something about the prospect of, what is the likelihood that this vertex is on the path, of A shortest path. That is, it's supposed to help you determine that. Yep.
I don't think I quite understand. So with the heuristic function Sx, doesn't that by definition find the shortest path? Because you need to find a value that you can't exceed, and whatever that lowest number is would be the shortest path.
Okay, say that one more time.
The heuristic function S of x, when you are discovering it, to find a minimum value that you can't exceed.
Well, it is, but that's not the case. Okay, let me just take a step back and give you a actual scenario of how we define a heuristic function, because this one is completely man-made. I mean, this is completely artificial. So what we'll do is we're going to switch back to Google Maps. And once again, let's go to San Francisco. And we go to downtown. And okay, there we go. So the heuristic function is basically something that is easy to compute, and it is always an underestimate. Is that okay? So if your algorithm is dealing with maps like this, which is planar, it's easy. You just look at the actual distance between 2 points. That can be your heuristic function, because that is always less than or equal to the actual distance to go from one point to another point. Is that? That is correct. Yeah, because the direct line connecting 2 points is always, the length of that line is always less than or equal to the actual route that you have to take in order to go from one point to another point. Is that making any sense? And it's also easy to compute, because once you have the coordinates of every single point of all the vertices, the computation of the actual distance between 2 points, like a straight line, is very quick to compute. But it gives you an idea of, are we going in the right direction, so to speak. In other words, if I want to go from here to here, okay, it's unlikely that I want to explore a vertex all the way over here. Now, in the case of San Francisco, you kind of have to, you will see that it will go out a little bit because of one-way streets and so on and so forth. So it will go out a little bit because, the right-hand turn thing, and, one-way streets. But it's not going to go all the way to Oakland. If you want to go from this intersection all the way to this intersection here, vertices, that is like, in Oakland, it's not going to be of any interest, because the heuristic function, it would basically say, that's the wrong way to go.
But in the case of like a map here,
Mm-hmm.
X,
You mean the actual graph? Okay.
without like a coordinate plane drawing on that, right? Other than just kind of
There are still ways to do it. Basically you have to find it. Okay, you have to find a way to quickly compute a function that is always guaranteed to give you a value that is less than or equal to the actual path. So if it's not planar, it has other properties that you can use to say that, oh, okay, this is a quick way to compute and underestimate length between these 2 points. Mm-hmm.
Could you also assume that from S to X, could you assume that they are connected by one edge that is shorter than the actual shortest distance? And
One edge that has a distance that is less than,
the shortest distance, like 5 and 1 going through E, would be short, the kind of one of those, like eyeballing it.
yeah,
But if it's just one S to X, it would have to be something like shorter or
it will work. I mean, the A star algorithm will work in both cases. In other words, if I draw one straight edge from S to X, if it is the actual shortest path, it will find it. If that one single edge actually is longer than the other paths, it will find the shortest path as well. So if you're curious, we can always just include that edge, which goes all the way from S to X as a single edge, okay? But it would be kind of not fun to make this, the actual shortest path. So let's make this not the shortest path, right? So we'll say this one has a distance of 20, okay? And A star will figure out that, oh, okay, even though it looks like it, even though there's only one hop, the actual length is longer than the other ones which have more hops. Yep.
If we want to apply this to neural AI or just regular AI, how would you go about it? Like if you wanted to put this into the code and want to try to make like try to program artificial intelligence or any type of neural
Well, this is, a form of AI. I mean, because it is trying to find the shortest path. So it is a classification of AI. It is actually, interestingly, this is called strong AI as opposed to weak AI. Neural net is considered weak AI, if I remember correctly. Um, yeah, because there are two types of AI. One is rigid, which is kind of like math and rule based, and the other one is kind of soft, which is kind of like, okay, we'll have the program to learn from patterns, and then we don't even understand what is being represented by the values, but it can do certain things that seem to be intelligent. So if you look into strong versus weak AI,
So as you say, there was two
I
types of
think
AI.
it's a different thing.
is a different
I
thing.
think strong AI has to. It's more of like a yeah, like kind of like actual.
Okay, so I got it actually reversed
No,
in
no,
that.
I think the actual comparison is completely like weak AI is like machine learning, just a predictive thing,
Uh
and
huh.
AI is more like Turing machine, like it actually has like general, like it says there, like general intelligence. I don't remember.
Well, let's
Well,
read.
like for like a neural network, right?
Uh huh.
It can only learn off of what you trained it. It can't like generalize. Like if you give it something that it hasn't
No, no.
seen
Well,
before.
actually, that is a neural net actually does generalize. It just cannot extract what it has generalized. It does actually
It
generalize.
does, but
Oh
like
yeah,
let's
it is
say
the opposite.
if you feed it a bunch of pictures of like bees, right? And then you give it like a bee that's like upside down or something.
Okay. So I think the broader definition is weak AI is very specific, and then strong AI is more general, and that makes Dijkstra's algorithm and A star. If you consider those as AI, that would be very weak AI because it is a very specific application. It can solve certain problems that we can solve, but it's a very specific thing. Playing chess is also weak AI because we do we just play chess? No. So strong AI, on the other hand, would be things that are much more general. So the more general it is, then it's called stronger AI.
What you call the strong AI and weak AI again? You said the
Strong
distinction.
AI is machine with consciousness, sentience, and mind. So that makes it kind of more general. It basically behaves more like a person, I guess. That's yep. Consciousness, not conscience. We do want conscience too, but it is not a part of the requirement, which is the problem.
And what was strong AI?
Hmm?
And what was weak AI?
Weak AI is a very application specific thing. You can solve a problem really fast, but it's only that problem. Yep.
So would it be strong AI is a self-learning AI that can
Um,
basically play any kind of video game?
it doesn't really say that here, but a technology that can learn to do different things would be stronger than a mechanism that can only be applied to solve a particular problem. So A star, Dijkstra's algorithm, those are all weak AI because you have a very well-defined problem. We got vertices, we got edges, we got distance function, we may even have a heuristic function. And how do I find the shortest path from a particular vertex to another vertex? That is extremely specific. Okay? Playing chess is also very specific because the rules of that particular game or that particular, yeah, it is game. It's game theory. Is also very specific. On the other hand, neural nets are stronger because a neural net can be trained to recognize different things. Now, if depending on what you train a neural net with, it can basically it can be used to recognize shapes. Okay, you can say, oh, that's an airplane, that's a horse, and so on. It can also be used to make decisions. Okay, you basically say you train it with, given this scenario, this is your action, this is the outcome, or a number representing the outcome. You give it enough samples, and you give it a new scenario that it has never seen before. It will be able to tell you, yeah, I think we should do that. That's very general, because now what you train it with um, can be buying. Which stock should I buy at this point? Okay, or what is the strategy that I use, that I should use given the current scenario. Okay, so how do you describe the scenario? You can describe the scenario using various indexes because you have to have numbers to represent all of those things. But nonetheless, it can be applied to a number of things. So neural nets are definitely on the strong side of AI, and then algorithms, any type of algorithm such as A-star and Dijkstra's algorithm are kind of on the weak side of AI. Is that okay? Making any sense at all? Okay. Cool. All right, so getting back to our example, which is this one. Now we're gonna track it down, okay? Find out exactly what it's gonna do, and this is gonna be this will take a while because we got well, I guess I used too many vertices here, but all right. So we'll go ahead and start a new spreadsheet. I'm not sure whether we'll have enough time to do this to finish this, but we'll try. Well, that's the best thing about the way I trace algorithms is I can stop, at the end of this class, but because, when I stop, it has a full state of, where the algorithm is at. We can just pick it up on Monday and continue. Or turn it into your homework assignment. Okay, so cisp440. And I'm going to put into the share folder, just so that you guys can find it and use it if you want to. And we'll name it using the same convention as last time, which is the date plus what algorithm it is applied to. I'm checking my mic, just to make sure that it's not running out of battery. And we'll rename to 2018-0425, I think. And this is the A-star algorithm. Okay, so the document is now created. You guys can actually go in and look at it. We need to track quite a few things this time. We have O as a set instead of Q, just a slightly different name. We have the previous function. So the previous function, I'm just going to use one column to track it, and then we'll deal with the representation later. We got the G function, we got the F function, and let's see. Oh, we also have T as a local variable, so let's keep track of T as well. So all of these are the things that we need to track. I'm not using a column for each particular value because that would take up like way too much room. So this allows me for a much more compact representation. Okay, so this is the trace. Let me look up where's the algorithm. Okay, here's the algorithm. So we'll put these next to each other. Okay, so it's easier to switch between these two. Or I can just kind of drag it. I can't. I want to turn it into its own window. Oh, okay. There you go. Cool. All right. So maximize this. Switch back to. Uh-oh. It's just being very, very slow right now. Okay, switch back to the. I can see my hard drive light just kind of staying on constantly. Just because I want to maximize the screen. And then we have the graphical representation of the graph. Okay, there we go. We got it. So we want to do some initialization. 3 things to initialize per vertex. The G value, the F value, and the previous value. Okay. All right, so we just have to remember that S is the start, X is the end, and then in between we have A, B, E, J, K. There we go. So we now go back to the trace here. And we just have to say, okay, how are we mapping these things? How do you want to represent this? Because if I say, keep saying previous of S is undefined, this is going to take the representation is going to be pretty long. Would this work for you? If I just say, S maps to undefined, A maps to undefined, B maps to undefined. In other words, I'm looking at a function as a set of two tuples. Would that work? Okay, all right, so we'll just use this. So A, B, E, and then we got J, we got K, and then we got X. Sorry, say that one more time. This is the previous function.
No, there's a tuple where you did undefined as UNF.
It's undefined. Huh?
No, there's a U and D.
There's like everywhere you have U and D and one.
Oh, okay, I see. Okay, I got a typo. Okay. Undefined. Okay, there we go. And then we'll also make this wrap around. Okay, so this way, I don't need to take up too much width this way. So we'll go to.
Double click on the side of the column.
That's going to make it too wide. Exactly what I don't want it to do. So we go to Format, and then we go to, I think it's under Align, or not. Oh, text wrapping. Yep, we just turn on wrap here. There we go. Okay, so now we can move on to the G values. The G values are pretty easy to deal with. The only thing that has a non-infinity G value is going to be vertex S itself, because it is at a zero distance from itself. So S has a 0 value. Everything has infinity. So this is INF for infinity. B is mapped to infinity. E is mapped to infinity. J is mapped to infinity. K is mapped to infinity. And X is also mapped to infinity. So this is from a different perspective compared to Dijkstra's algorithm. So turn on wrapping again. There we go. F is pretty much the same thing, or almost exactly the same thing, except for one item, which is S. Because S is supposed to use the heuristic function, which I remember as 4. So that's it. Are we good so far? T is a local variable. We don't need to get to T at this point, so that's cool. O is just consisting of the initial or the start vertex. Okay, so it's just one single element in O. So that's our start state of the entire algorithm. Okay, is that good so far? Okay. And I'm going to do the same trick here to keep the header, and then we can make these columns slightly wider so we can reduce the amount of wrapping that we need to do. Okay, cool. All right, so now we can go into the algorithm. So the algorithm is here. We are done with initialization, so now we are at the while loop part. Well, first of all, O is definitely non-empty. It satisfies the first condition. Now we look at the second condition. Is there at least one vertex of the entire graph so that its F value is less than its G value? So we look into the spreadsheet again. So let's see if I made a mistake here. The F value is less than the G value. Oh, I cannot use that, huh? Because that condition is not true. We are supposed to get out of the loop. Well, the reason why it doesn't work is because infinity cannot be compared to infinity. So technically speaking, it is true because infinity does equal to infinity. And then the condition is looking for less than or equal to. Less than. Okay, that doesn't work. The F value is less than the G value. Or G of X to be specific. Okay. No. So I was wrong. I didn't read the question carefully. It's G of X. So G of X is infinity. F of S is 4. 4 is less than infinity. So we got hope. Is that okay? Okay, let me just go back and reiterate why there's hope. Okay, right here we're asking, can we find at least one vertex v so that f of v, the f value of v, is less than the g value of not v, but x specifically. So we go back to the table, we look at the g value of x, it is infinity, but then we look at all the f values. One of the f value is 4, it's not infinity. So so there's hope, we can actually proceed. Okay, so after we proceed, I need one column to specify which vertex I have chosen. So insert one, and I need another one for the neighbor. So we need to insert 2 additional columns because this one is C, the vertex that we have chosen, and then this is the neighbor of C that we are considering. Okay, and these two do not need to be very wide, but probably not that narrow either. Okay, so which vertex should I choose as vertex C in the algorithm? Okay, let's go back to the algorithm and find out. So we are at this point here. I'm saying, okay, pick one C out of O such that the f value of C is the smallest of all the vertices in O. Well, we only got one vertex in O, so that has to be the only choice, right? So now we go back here and we say, okay, let's pick vertex as the vertex that we want to explore, which also means, O is now without its only vertex, but we'll put something back into it soon enough. And then in the algorithm we have to explore all the outgoing neighbors of vertex S. So for that we're going to switch to the tablet and we go like, okay, what are the outgoing neighbors of vertex S? We got a bunch, we got 4 of them, right? So we have to evaluate every single one of those and then decide whether to do something with them or not. So let's start with vertex A. Okay, so vertex A is the first outgoing neighbor that I'm considering. By the way, this order is not important. Okay, you can go in any order as long as you explore all 4 outgoing neighbors of S, it's fine. Okay, so once I have chosen this, okay, now I have to make these columns narrower again because I need to get to the T column. Okay, so now I have to define what is the T value of vertex A. So switching back to the graph representation, my question is, if I go through S, from S to vertex A, what is the shortest path? Well, it costs me 0 to go from S to S, right? And then the edge to S, from S to A is 3. So the shortest path known at this point from vertex S to vertex A is going to be 3. It has a length of 3. Okay. So we go back to the table and we say this T value is 3 at this point. And then we do the comparison. We are basically asking the question, okay, so let's go back to the algorithm first. So then the condition of the while loop here is to say, is T less than the G value of A? Okay, let's compare. T is 3 and G of A is, this is the G of A is infinity. Is 3 less than infinity? Yep, so the condition of the conditional statement is true. Now we go into the conditional statement. So in the conditional statement, we got a few things to do. The first thing is, let's go ahead and add A into the set of uppercase O. Okay, so let's do that. So now we have A in the set of O. What else do we have to do? Let's check. We want to mark the previous vertex of A is S. Okay, we can do that. So we go to the previous function. So I'm just going to do the copy and paste and modify thing. So we look at this one and we specifically only change the previous of A is S. Is that part okay? And we also have to adjust the other 2 functions. So we look at the G function and say, that's an easy one. We just use whatever T is and put it into G of N. Okay. or g of A in this case. So we copy and paste the g, the entire thing, and then update only the entry for A, and it's going to get the value of 3. So we change the infinity associated with A to 3 as a number. And then we have to make some adjustments to F as well. So I'll just do a copy and paste first, and then go back to the algorithm to find out how to update the F value. The F value is basically the same as the G value, which is T, plus the heuristic from vertex A to vertex X this time. Okay, so it's going to be 3 plus, okay, let's go back to the graph here. So right here we have HAX is 2, so it's going to be 3 plus 2, which is 5. So we go back to the trace, and then we change the value associated with A to be 5. Like that. Is that okay so far? Okay. We're not even done with the for loop, because we have 3 other outgoing neighbors to consider. Okay, going back to the graph, second outgoing neighbor to consider is E. Okay, so let's go ahead and pick up E. So now N is E, an outgoing neighbor of vertex S. And then we have to reevaluate T. The algorithm says, okay, T is G of E in this case, plus the distance, G of S, which is 0, plus the distance of the edge going from S to E, which has a distance of 5, so T is 5. So we go mark this down and say this is 5. And then the conditional statement has to evaluate the condition. The condition that we need to evaluate is whether T is less than G of E in this case. So we go back to the trace. G of E is infinity. And T is 5. 5 is less than infinity. So we go into the loop. The first thing we do is we add E into the set of uppercase O. The second thing we do is to update previous G and F. Previous is easy to update. We just go to vertex E and say, okay, your previous is no longer undefined. It is vertex S, which is our start vertex. We go to G and we update E, the item for E. So it is 5. In other words, we know that the known shortest path, the length of the shortest known path from the start vertex to E now has a cost or distance or length of 5. And the F value is going to be updated as well. But to update this one, I have to look up the H value or the heuristic from E to the destination. It is 1, so 5 plus 1 is 6. So we update that to 6. So E now has a F value of 6. So once again, I just want to kind of repeat it. I know I'm nagging. The F value of 6 associated with E is basically saying if we go from the start vertex S through vertex E to the destination, I'm guesstimating that shortest path is going to have a length of 6. That's what the 6 is. Okay? So are we doing okay so far? We're running out of time, but I'm hoping that you guys got the general idea of how it works. So the idea is once we're done with the for each loop, the uppercase O set is going to have 4 elements at that time. And then of the 4 elements at that time, we'll look at the F value and we pick up the one that has the least value. Basically, we're saying, okay, we're being greedy. Whoever seems to be the most promising vertex to go through to the destination, we'll pick this one and explore a little bit more to find out more about that quote-unquote path that we think is going to be the shortest. So that's the general idea of the A-star algorithm. And you can see how the heuristic is influencing how we choose which item from O to explore first. So without the H value, if your H value is always going to be 0, then the whole thing boils back down into a breadth first search. It is all based on how far is have we gone from the start vertex to each individual vertex, but we are not taking into consideration, I am guessing from here to the destination is going to be about this much. All right, so I'm going to stop the lecture. I'm going to give you the assignment for Dijkstra's algorithm sometime today. You have 1 week to do it. It's basically the same thing that we did in class. You just have to kind of put it into a spreadsheet format. So there's that. All right, so I'm going to stop the recording. And if I don't see you, have a nice weekend.